First of all, welcome everyone to my talk. I know it's one of the final talks for today, and it's really good to see so many number of folks today joining for my talk. I'm Shivay, and of course, I'll be giving a brief introduction about what I'm going to be speaking about as well. And so it's going to be fun because it's a fun topic and a lot of new concepts for a lot of JavaScript folks. So I hope that everyone is able to at least get to learn something from today's talk. So, well, the talk that I'm going to be presenting is powering up Node.js performance with Rust and WebAssembly. So right off the bat, what you'll probably see are two relatively new terms today in the entire web industry, and that's with Rust and WebAssembly. So I'll be also demystifying some of the general concepts that people have with respect to languages like Rust and also concepts like WebAssembly today. And we'll see how you can combine the uses of all these three to make really highly performant applications. Very quick introduction about myself. I'm Shivay. I'm a developer advocate at Meilisearch. It's an open source Rust-based search engine that can be used to create very quick full text searches that you can include in any kind of an application. And I'm also a contributor at Layer 5, which is an incubated project under CNCF. And you can also follow me on Twitter or @howdevelop in case you want to connect with me. But moving to the topic itself, well, I wanted to first just cover some of the general software concepts that we have today. And if we look specifically at the Moore's law, right, we generally see that essentially what we have today is that whenever we look at the general hardware space, right, and we see that over the past few years, the number of transistors have been increasing, and we have sort of come to a plateau effect where if you see that the number of transistors that you can fit inside of a small chip, that cannot increase exponentially, right, that we have seen previously. And what that means is that there is a general need to overcome that limitation with the help of software. So how can we optimize our software so much that we can overcome this hardware limitation that we have seen? And that's actually going to become a lot more apparent as we move and we proceed further. So the need of the hour is to improve the software performance. And also what we have to take into consideration is that whenever we talk about improving the software performance, it has to also be safe and secure. We just cannot go ahead and improve software at the the effect of having bad security. We also need to ensure that we have good security in place as well. So that's where certain tools like Rust, WebAssembly actually come into the picture. So what is Rust, right? Of course, Rust was a relatively new language introduced back in 2015 and during that time, and it's still supported by Mozilla. But as compared to some of the other languages like C++ and C, which today are really huge, right? They have been there for more than 10, 20 years. So why to choose Rust over something like C++? So if you compare Rust and C++, both of them are very highly compliant in terms of performance and also in terms of the developer adoption today. And both of them have really great communities. But one of the key areas where Rust overcomes or sort of overperforms C++ is in terms of the error prone. So of course, we are well aware of the common issues within C++ with respect to memory management, with respect to pointers, right? It's a very huge thing, right? So that's where Rust really is capable in terms of the memory management and also becoming a lot less error prone as compared to C++. And that's one of the reasons that why we would want to actually use Rust. Now, of course, we know that the standard V8 engine today that we have in Node.js that has a C++ compilation that takes place behind the scenes. So today, what we're going to be seeing is that how you may actually use some alternate runtimes. And that's what we'll be introducing in some time. But coming to the next point, and that is also speaking about like how you can actually run Rust inside of the web. Because of course, what the idea is going to be is that we want to essentially take some of the highly computational tasks that currently run in Node.js, and we want to offload those tasks into Rust. So if we look at the historical background and how we were able to actually run Rust inside the web, so essentially what we used to do is that we used to compile that into native libraries and then run them as extensions with the existing runtimes like in Node.js. But this approach proved to be really unsafe. So one of the modern ways in which we can actually do that is that we can essentially take our Rust code and compile it to this kind of a byte code, and then actually run it inside of a virtual machine like that, for example, in case of WebAssembly. So just to sort of give a very basic introduction about WebAssembly itself, a lot of you might be aware of what exactly WebAssembly is, but just for those folks who are relatively new to what exactly is WebAssembly, so essentially what you can think of it as a binary instruction format. So we are going really deep into assembly language and how, like, machine code actually gets compiled. So just think of it as a binary instruction format that usually will deal directly with your assembly code. And essentially what we are doing is that we are taking the code or the source code of, like, let's say a modern language like C++ or Rust, and we are compiling it into this executable bytecode that directly will deal with the lower level hardware or the lower level abstract layer inside of your operating system. And one of the general conceptions about WebAssembly was that it's just for the web browser, because if you look at the two terminologies, that is web and assembly, a lot of you might think that it's just for the web. But to be honest, like, it's not just for the web. Today, the ecosystem for WebAssembly has grown beyond just the browser, although it was initially created to be run alongside JavaScript in the browser. But today, it has a lot of applications beyond just the web. And it's used in server side, it's used on edge devices, right? So that's where we are also going to be seeing how you're actually able to use WebAssembly with Node.js for running any kind of server-side implementations or server-side applications. And no, it's not just, like, limited to being able to run with C++ or these kind of high-level languages. You can also use it with scripting languages today, like Python, JavaScript. So essentially, you can actually run JavaScript inside of WebAssembly today. And we'll also look at some of those use cases as we expand into our topic today. So today, WebAssembly is also used for a lot of edge applications, especially when you are talking about very less resource-intensive applications that you want to run on the edge. Now, those could be microservices, those could be Dapper, and also, like, like, let's say running machine learning on the edge. That's where WebAssembly really shines, as the standard containers, right? They are very, it can take a lot of time to actually run and invoke your standard containers. But when we talk about WebAssembly containers, those have a very small blueprint in terms of the size, but also in terms of the startup time. So that's one of the great areas why people are actually looking into the WebAssembly ecosystem as compared to the standard Linux containers to be able to run and invoke applications. And that's where I would love to introduce the WebAssembly runtime, and essentially what exactly the WebAssembly runtime, or Versamatch. It's essentially an open source project today that is currently incubated under the CNCF landscape, the Cloud Native Computing Foundation landscape. So it provides the runtime for WebAssembly applications and can be used for a lot of different applications, again, running microservices, running machine learning inference on the edge, and then even for, like, any kind of a blockchain-based application as well. Now, one of the greatest advantages of the WebAssembly of Versamatch specifically is that as compared to the other runtimes, it actually uses something known as ahead-of-time compilation. So that is what is one of the biggest reasons why it is so highly computational and really fast, because of the ahead-of-time compilation. And of course, it is very lightweight and portable, so you can run it across multiple, like, on Mac, on Windows, or on, like, even your Arduino, right? It can run across multiple operating systems as well. So it's highly compliant with any kind of an operating system as well. So essentially what we have come to is, after having introduced all these different tools like WebAssembly, Versamatch, and Rust, so what we want to do is that essentially we want to stick with JavaScript because of the ease of use of JavaScript. But what we also want to do is that if we want to make really highly computational applications, we want to sort of offload some of the tasks that Node.js is currently doing, to also include things like Rust and WebAssembly. So with Rust, we'll be getting the performance of Rust. And with WebAssembly, what we're going to be getting is a very secure environment, because WebAssembly is really secure as compared to any other type of. So usually what, to sort of explain this into a lot more depth, is that WebAssembly, as I mentioned, is a binary instruction format. So by default, WebAssembly cannot do anything on its own. What we have to do is that we have to essentially invoke the WebAssembly module to be able to actually run something. But in the entire architecture of how WebAssembly works, it's highly safe, and that's what we're going to be providing with this WebAssembly runtime. That will provide your application or whatever kind of service that you're running a very secure environment as compared to other type of runtimes. And we'll just go over briefly the architecture over here. So as you can see that by default, whenever you're running any JavaScript applications on the front ends, of course, you'll have a front end where it's interacting with the browser. Now, when it comes to your backend where you're running a Node.js application, the standard runtime compiler, for example, the V8 engine, that has a C++ based runtime. Now, what we are proposing is to have an alternate runtime, and that's your WebAssembly based virtual machine. So what will happen is that, for example, and I'll be showing a real world example over here as well. Like let's say that you have a Rust-based source code. So what we'll be doing is that all your highly computational tasks, for example, if you're doing machine learning inference with Node.js, so we know that machine learning is really highly computational, right? And very compute intensive. So what you'll be doing is that you'll not be writing your actual machine learning inference code in Node.js. Instead, what you'll do is that you'll be writing your machine learning inference code inside of Rust. And what you'll be doing is that you'll be making a call via your Node.js function to this WebAssembly runtime. And what it will do is that it will help compile your Rust code into a WebAssembly executable or a bytecode, and that will run inside your WebAssembly ecosystem, that your WebAssembly virtual machine. So essentially what we are doing is that your Node.js function is just calling your WebAssembly runtime, and all the highly computational tasks are being managed within Rust and having the security of being run inside the WebAssembly virtual machine. Now, your WebAssembly virtual machine has access and can basically get access to your file system, to your to the hardware. For example, if you need to access the GPU, so all the physical resources can be accessed directly via the virtual machine, by the WebAssembly virtual machine, and also, as I mentioned, to your OS as well. For example, if you want to get some of your files that will be used during the training. And like, let's say once you generate a response, that can be sent back to your Node.js application in order to do any further implementations that you want. So everything with respect to file management, with respect to accessing hardware resources can be directly managed via this WebAssembly runtime. And that's what makes it really exciting. And this is what I just spoke about, that you have your Node.js application, you have a JavaScript function, and that's calling your Rust function to compile it into the bytecode, and that's how your Node.js application will essentially communicate with your WebAssembly runtime. And for that, of course, I mean, having explained all of this architecture, the next step is how to get started, right? So of course, to be able to set all of this, you do need some of these things. For example, one of the ones, of course, the best suited example is to have a Linux distribution. Although today Versamatch is also supported very well with Windows and with Mac. So I'll recommend you checking out github.com/Versamatch/Versamatch if you are also using something like Mac OS, especially the Intel or the M1 Mac, and also if you're using Windows. So there is general support, but the best support that you can get is with a Linux distribution. So you could potentially also do something like, if you're having a Mac, you could install a Linux image on Docker and run your inference using that. But also you do need a Rust language, you need Node.js, of course the Versamatch runtime, and finally you also need the Rust Wasm compiler toolchain. This will be responsible for converting your Rust code into the Versamatch binary, the bytecode. So to get started, there is going to be a starter project that we are going to be cloning, and that's you can find that on github.com/secondstate. I'll be sharing these slides and the link, but of course you can take a picture of the starter code. But I'll quickly give a walkthrough of what exactly is included in this starter code and how you can get started, and of course the general idea of this demonstration that we're going to be showing to you today. So for that, I'll just quickly get this source code over here, and I'll just quickly share over here. So give me just 1 second. quickly go ahead and open up the GitHub repository. All right. So what you can see over here is we're going to be seeing two most important things over here. So one is the node folder, and the other one is the source folder. So if you go inside the source folder, you'll see one simple lib.rs function. It's a Rust function that we have created. And what it's doing is a really simple Rust function to show you the demonstration or the capability of what we want to showcase. So over here, what it's doing is that essentially it will, the first thing that you'll see over here is that we have added comment that this is a function that will be used to actually get converted into a WASM bytecode. And it will also generate some JavaScript function that will be used by our Node.js function to invoke the call to this WebAssembly function that we'll be making with the help of our Node.js function. But essentially, it's a very simple function that we have written where it is receiving an endpoint. We'll be making a request from our Node.js function where this will basically, like, let's say, we'll have something like hello world. So it will be accepting like a variable that will be used, and it will be appending it to hello. So essentially, we'll be making a request, let's say hello Shivay. So we'll be sending that request as Shivay, and it will be appending hello to Shivay to return whatever we are sending apart from hello. So that's what this Rust function is accepting. And apart from this Rust function, the other thing that we are going to be taking a look at is our node folder. So I'll just quickly go back to the source directory. And within this, we'll take a look at our node folder. Within this, we'll look at our app.js. So this is what is sort of the heart of the program. So at the beginning, what you can see is we're invoking this say function, which we are basically getting from our Versamatch Node.js starter library.js. So how this particular library is getting generated, or how this particular source code is getting generated, is that basically once we compile our Rust code, it generates two different files. One is the actual Wasm executable, and the other one is this Versamatch Node.js starter library.js, which will now be used by our Node.js function to be invoked. And that's where, if you see over here now, that inside of our function that we have written inside over here, right? So what we're doing is that we are sending the name that we want to invoke from our Node.js function. So this name will be sent to our Rust function, where it will be appended to hello. So if we were to, like, let's say if we had something like Shivay, so it will, the final result would be hello Shivay, right? So that's what we are doing with the help of this node function. So in a nutshell, what we're doing is that once we have this Node.js function, the first thing that we'll be doing is that we'll be compiling our Rust function to get our Wasm executable and also our starter Node.js function that will be used by our Node application, and we'll be able to make a call. And if, for example, now what we'll do is that once you get this running, we'll essentially get an output, like let's say if you're running it on port 3000, in this case, the port that we have exposed to is 3000. So if you were to make a curl request to port 3000 and send, like, let's say, OpenJS, so it will return hello OpenJS. A similar example that I would want to also showcase in terms of the machine learning inference that I spoke about is, I'll just quickly show a real-world example before I jump back to my presentation. And essentially, this is an example provided by Second State that supports the Versamatch runtime. So essentially, what we have over here is a MobileNet TensorFlow model, essentially that's used for being able to detect and recognize a lot of the common objects within a particular image. So what it's doing is that over here, all the machine learning inference that you'll see, right from the model getting the input file that we get and doing the machine learning inference and actually drawing the bounding box, all of that will be taken place with the help of our Rust function. So none of this inference will actually take place with the help of the JavaScript function itself, and it's offloading all of that machine learning highly computational tasks to our Rust function. So that's how it's acting in the behind the scenes. So just to give a very quick demonstration, I'll pick up an image and probably, like, let's say if I take this as an image, like, let's see what do we get if we classify this image. Okay, so let me see. Okay, it says rate limit exceeded. Well, I mean, real world example of demo getting failed. But the idea is that once you run this, what you'll see is with any machine learning inference, what you'll see is you'll see a bounding box created on the object that it detects, and it will basically give you an inference of, okay, if you let's say had an image of an bottle. So it will create a bounding box in front of the bottle, and it will let you know what's the end result, right? So it will do that computation for you, the machine learning computation for you, and it will be able to detect that. But the general idea is that all of this, this is just one example, right? If you had some more highly computational machine learning models, right, really large models, in order to save performance for your web application, because we know that there are certain resource constraints that comes with Node.js. One of them being it being not being multi-threaded. Of course, you can run multi-threading with it, but of course, in general use case, it is single-threaded. So we know some of the resource constraints that come with Node.js. But yes, essentially that's what this entire ecosystem is, and of course, it's still evolving. The entire ecosystem for WebAssembly itself, the developer experience related to WebAssembly is not the most ideal, but this does present a really great ecosystem that is possible with WebAssembly. And that's what I wanted to cover. And of course, I mean, the next slide is mainly just covering the entire code. But what I just wanted to showcase from this presentation is that you can use WebAssembly today with Rust, with Node.js, to really make the performance and of your Node.js application really quick, but also provide it a very safe environment to be able to execute inside of. But yeah, I mean, of course, there are a number of other different kind of use cases that you can use this with. Today, we had some of the presentations over the past couple of days where we spoke about event streaming in Node.js. That's also something that we are now looking at that you can actually manage with the help of WebAssembly. Today, we have a lot of different tools such as like Cloudflare and then Fastly, where they are actually using WebAssembly under the core, under the hood, to do all of different kind of highly computational tasks like serial management, right? That's some of the things that you can do with WebAssembly, and that's why I'm really excited, because I also work quite a lot with WebAssembly on the front end by contributing to a project known as Tensorflow Js, which is an open source machine learning library, and it supports multiple backends like WebGL, WebGPU, and Wasm as well, to be able to do machine learning inference on the front end. And so similarly, since WebAssembly is now not just limited to our web browsers, it has expanded, and it actually has a lot more number of applications on the server side as compared to the client side today. So that's what makes it really special. And if you are having any kind of use case within your Node.js application, the ecosystem is still evolving, right? It's not evolved, and it's not at a stage where you could get into production by in a very short time. But what this talk really represents is that you should be aware of how you can manage the performance of your Node.js applications, and there are certain tools like Rust and WebAssembly that can actually help you achieve that in a very safe and secure manner as well. So with that in mind, that's pretty much the end, and that's the end of my talk. And I hope that you got to learn all about Rust and the WebAssembly ecosystem and how you can basically combine that with Node.js. I'll recommend you checking out the Versamatch project, and probably I'll just go to the Versamatch website just to give a very quick intro about the project, although I have done that already. But I'll just quickly go to the Versamatch website. And basically, if you want to contribute to Versamatch, it's a relatively young project as well. There's a monthly meeting that takes place, a community meeting that takes place for the Versamatch project every month on the first Tuesday. So if you are interested into the web ecosystem, Versamatch is not just limited to Node.js. You can also do server-side rendering with Versamatch, and there are a number of different JavaScript-based applications that you can actually do with the help of Versamatch. So of course, I discovered one of them, but you have all of these different other areas where you can actually use Versamatch and of course, the Rust implementation is one of those examples. But yes, it's an open source project if you are interested to contribute to it. And of course, with the help of this talk, I hope that you got to learn how you can actually improve your Node.js performance. So thank you so much, and I hope that you liked the presentation. And I'll be open to questions now. Yes. So there are multiple ways in which you could probably do this machine learning inference. If you just use native JavaScript, it could take, like, let's say 1 minute, 2 minutes. And I'll be more than happy to share some of these findings that were there. I have a few resources that I can share with you offline. And then there's another implementation where you could use just, like, let's say Tensorflow Js. That will probably do it in, like, let's say 10 milliseconds. But now if you were to do that with the help of Rust, that will come down to less than 1 millisecond. So that's the kind of performance term that you can see as you use the Rust ecosystem to offload those tasks. Definitely. So as I mentioned that today TensorFlow JS, the library, it has support for a lot of different backends. So one of the backends that we have is with WebAssembly. So it's already being used as a supported backend, and there is also like SIMD support. So one of the talks that you gave yesterday, that's like, that is there. So that support is already there for WebAssembly as a supported backend. Yep. Yep. Yeah, so I mean, of course, Wasm Edge is not just one of those runtimes. There are multiple runtimes. So where Wasm Edge, I would say, outshines Wasm Time or any other runtime is because of the fact that it has ahead of time compilation. That's one of the biggest factors to really make it very fast and very quick to do all these inferences, especially when you're doing it on edge devices, which are very computationally resource oriented, right? They have very less resources that you can work with. So that's one of the cases where Wasm Edge outshines some of the other runtimes that are there for being able to run WebAssembly executables. All right. Thank you very much. I hope you have a great rest of the this OpenJS world. Thank you.